continue. Engineering analysis. Now we've done all of these basically geometry. We were able to essentially connect them together, know what the linkages between each and every one of these objects are. Now we have to analyze it. Now we have to be able to identify what it is that we want to get at the end, and then analyze and get the responses of it. In our case, engineering responses and various different types of engineering responses, so that we would be able to make sure that the geometry and the other aspects that we've plugged into this can actually support our requirements and criteria. Okay, so you have your BIM, you have various different types of software that this basically plugs into, and it can provide you with the information that you want, and then you can get your engineering analysis at the end. So I'll give 4 examples: wind, solar, energy, and structural. I'm just giving these examples so that you can have an idea that if we model the same basically elements effectively, you can utilize it for multiple different aspects. And using that, you would be able to have some opportunities to understand how this particular design that you've completed is going to satisfy whatever constraint you have at the end. Okay. So wind simulation. For instance, I've done this simulation using flow design. Where is this going to be useful? Obviously, in areas that wind is going to be of essence. Mostly, wind is going to be of essence if you have a taller building. So you have some, let's say, the fundamental frequency there becomes important because it's a dynamic type of loading. And with that, taller buildings normally have, lower in terms of those fundamental frequencies. So we want to make sure that whatever we're designing is going to satisfy what we have at the end. Here, so we can simulate it and, for instance, see by means of different types of velocities that those velocities have to actually comply with the conditions that we have in that particular site that we're going to be modeling and we're going to be completing, right? So that's the whole idea there. Now we can change it. You can change the direction. You can do it in different locations and different means, and then from that you can take it from there. Okay, you can also, and why is this also important? Also, sometimes when you have, let's say, urban areas, you're going to get situations where you have wind tunnels that are created, and sometimes these wind tunnels are of significance. So you need to be able to design for that as well. Anywhere where you have some sort of, let's say, situation, for instance, the same thing with earthquake, for instance, that we have. If you have an earthquake-prone region, you would have to be able to design it for that, or you design your structure based on that. For instance, in terms of pressure, you would be able to know and get a pressure profile of what is going to happen. And this is in 2D. You can perform this in 3D. Again, there's a lot of back-end analysis and back-end basically calculations that need to go into this in order to make sure that our simulation is correct. Why this becomes important is because if we cannot and if we do not know what we are going to be expecting based on whatever load there is that we're applying in this case, or whatever, let's say, preliminary conditions that we have basically provided to this model, if we cannot identify that, and if we do not know what the realistic expectations in terms of its response is going to be, we are not going to get accurate results. That's the whole point. That's why some of these engineering software are also good. However, unless we know what that software is going to be doing, how it's going to be calculating it, it's going to be quite challenging for us to be able to recheck and identify it. That's why your role as digital engineering and construction consultants in the future becomes important. How I see the future basically of this area is more customized software in order for us to be able to communicate and identify specific, let's say, characteristics and specific customized solutions. And that's how you can also have in your, let's say, consulting firm a bit of a more, let's say, competitive advantage. Okay, if you're all using the same simulation software for your wind that does the same thing, you're not going to have any type of competitive advantage. And I could tell you by experience that there's a level of uncertainty and there's a level of, let's say, error that exists in each and every one of these, because these are solved for the most part numerically. Okay, so that's also something to keep in mind. That's why we have all of these, let's say, researchers in structural engineering and various different fields basically trying to minimize the uncertainty that we have so that we can generalize our solution to various different aspects. Something like aerodynamic analysis, it's not, let's say, a field that has already been solved completely. There are still some bits and pieces that need to be taken under consideration there. Okay, so there's something to keep in mind, and you're going to be seeing it, let's say, when you're doing your analysis and the optimization of your design. You're going to observe that each and every one of these variables and thresholds, when they change, your final design is going to change as well. So each and every one of these can also be optimized and fine-tuned. Okay, so it's something to keep in mind. So how can we even identify that? Again, our boundary conditions and our initial constraints. We need to know where our site is. Based on that, we need to know where we can find the proper information in order for us to simulate this particular problem correctly. That's the whole idea, right? So for instance, in this case, you have the ASCE. Are you guys familiar with the ASCE? American Society for Civil Engineers, yeah? So that has basically some information specifically for the US. You have that. Based on that, you can have some expectation of the average of what this load is going to be. And then from that, you can simulate using whatever interoperable program that you have that's going to be accurate, that you've decided, what would be the final responses on that. So each and every one, that's why information modeling becomes important, because each and every one of these would have some sort of constraint that would be added to the problem. And for instance, if I want to design for wind in Los Angeles, is going to be different than Karlsruhe, is going to be different than Calgary. Okay. Same with snow loads. It's the same topic. You can have that, and here you can go to this basically software provider Dlubal. In the past 2 semesters, I invited them to give some lectures. This semester, I decided not to, but you can still. I've provided the lectures for you to take a look at it. They also have a website which is quite good and interesting, so that you can go through basically for different codes, and using different codes, you can see the severity indices of, let's say, different types of loading. You can do wind, seismic, snow. Based on that, you can actually design it that is compliant with the code that is going to be regional and acceptable. Because if you don't do it based on that design, obviously your design wouldn't even be accepted and your engineering wouldn't be correct. Okay, so that's the whole idea. What you need to do is you need to know what you're designing, where you're designing it for, and what are the uncertainties that could actually happen in that, and what aspects you need to take under consideration. And something as standardized as, let's say, loading for structural analysis, for structural responses, still has some complications that you need to take under consideration, let alone all of these other engineering disciplines that you want to perform at the same time and get the responses. Okay, make sense? Yeah, okay. Solar simulation, we did a simulation here as well. Again, location is important, weather information is important. Can we say that because the average is this much that we can always expect this? No, right? So what we design with is some level of uncertainty, right? But we need to know what that uncertainty is. If I just rely on this and say this is it, and end of story, I'm not doing justice to the amount of uncertainty that exists and variability that exists even from year to year. Okay, as engineers, what we need to know is what these variabilities are. We need to break down the problem and know exactly what is going to happen. How can we do this? By acquiring better and more data, by knowing how the problem is solved. These tools can only provide you with judgments on how complex calculations are done very, very fast and very, very easy. It does not take away from what you as your engineering judgment, you as the digital engineer needs to know. I'll give an example of this. There was a library that was a very, this was one of probably the first BIM projects that I had, I think it was around 2010, 2011. And this library, so in Calgary, for instance, it's a very cold environment. You get snow, once it's snowing, it's so cold that the snow never melts. But then, surprisingly, you get these winds that are warm in terms of its nature, and it changes the temperature from, let's say, minus 30 degrees to plus 7 degrees, plus 10 degrees for 2 or 3 days. So all of the snow melts. So you typically get 2 or 3 snowstorms that stays, but every time, you get it to melt a bit using this. What ended up happening for this library was that whatever the mechanical engineer was doing there was not taking under consideration these types of variability. And they designed one of these drainage pipes an order of magnitude less than what they were supposed to. So if they do not know how this is going to be done, and that is if we assume that they actually didn't know about this. What if they knew about this and then tried to model it, but then the computer provided some information that they could not go and recheck? So there are two sides to this, right? One is that if we do not know the environment that we're designing for, and we're not taking under consideration all of the aspects that need to be taken under consideration. The second is, even if we think that we are, how do we know that the final design actually is going to satisfy that? Okay, so the validation part is important. Your engineering judgment is important. An order of magnitude, that means 10 times less, right? So that means that if the person or if that entity would have actually thought about this, looked into this in more detail, they would have been any engineer that has been working in this field for a few years could know that this might be 2 or 3 centimeters here or there, but not 10 times, right? So that's how much we can rely on this also becomes important. That's again where the customization comes into play as well. You guys, how I can envision it, you're playing around with your ChatGPT, telling it what to do. Each and every one of these basically platforms would have that. You have your customized way of basically building your own software, but you know exactly how the calculations are done, what the functions are, how is this performed, what the numerical, let's say, uncertainties are, what the optimization strategy is, and so on and so forth. Because you, as the engineer, know how it is, you know how to break down the problem, you know how to perform the analysis. Now you just need to convey it to a computer that can understand it. This is how in the next hopefully 10 years, unless we blow the whole thing off, we can envision our industry to go forward. Okay. Energy analysis. Again, we have built-in software through Revit. You would be able to do that, and it would do a cloud-based analysis. Again, the level in which we can rely on this information also becomes important. However, if we have that, we would be able to do a few different types of analysis, and we would be able to know, let's say, how much the yearly usage is based on, let's say, the average household, let's say, cost for energy. You can get some average number there. Again, this is average. If you want to get a better idea about it, it has to be more local. You have to know exactly what the variations of the market is going to be, and so on and so forth. What does this mean? This means that whatever problem we're solving, we need to know exactly how it's going to be solved. If we do not know it, whatever information we're getting from this is just going to be basically me Googling something and getting some answers from someone over the internet. It would not have any difference. This is very important for us as engineers to actually understand that these are just tools. They are not God, let's say, they're not going to provide you with something that is unquestionable. The only thing that you can know for certain is that if you know completely what the boundaries are, how these calculations are carried out, using that, you would be able to get the results that you want. If you do not know that, there's going to be some variability there, right? Sometimes you can always test it and validate it based on the data that you have, so that you can know that, let's say, the software can provide these solutions with this level of accuracy. You can always do that, and that is a part of the engineering as well. That's why some softwares are a bit better. Some other softwares, let's say, Abacus, you would be able to perform finite element analysis and do the modeling yourself there as well, and you have quite a bit of flexibility and freedom as a structural engineer. Some other ones, you can just put together bits and pieces of it and then try to kind of get a final result that you think is going to be good, and then you can do a more detailed engineering. Each and every one of these tools needs to be known where it has to be used, and it has to be with respect to the type of information and type of analysis that you want to perform, okay? Structural analysis. So for instance, this was another example of the deformed versus undeformed shape. This was a particular project that I was involved in. We wanted to see, these were some temporary bracings there. They had installed all of these, and these are very large cantilevers. So I think one side was 25 meters of cantilever, the other side was 16 meters. Then they took one of them off. They needed to know what this displacement is, and with that displacement, they needed to know whether that is within the tolerances that they could expect, because afterwards, once this particular skeleton was built, which the most of it was prefabricated, then prefabricated actually windows came around it. And those windows were basically, they had what we call a very long lead time. That means that it needed to be ordered and then assembled to custom, and that particular customization took like a year for them to be able to do that. They needed to know this way in advance to make sure that whatever window they're going to order or they have already ordered is going to actually properly and in a stable way attached to this, so that the load is not going to increase, let's say, the deformation of the window, because the window is not supposed to be taking the load, right? That's the whole idea. But through that, for instance, I utilized SAP 2000 and did some analysis there. In order to do that, we needed to collect some point cloud data to know what the real, let's say, displacements are and what the analysis is providing, and then see if they comply or not, okay? So I'll give two examples I again told you about. One is the clash detection. My hope is that if we can do this properly, and if we know what the linkage between different objects are, we do not even need any type of clash detection, but we're not there. And quite frankly, in order for us to get there so that we can build a bit more intelligence, we need some, let's say, intermediary transitional, let's say, tools so that it could support us. Why? Because once we have some of these, you know, thousands of these, millions of these initial designs that we know do not clash, we can then try to train some sort of neural network, generative adversarial network, so that it could provide us with some more creative means of better results. But until then, we need some sort of transitionary, let's say, tool and software. So this is for clash detection, the other one 4D scheduling. And the reason why I wanted to talk to you about clash detection is that with Navisworks is quite simple, actually. You put two of these models together there, and then using that, we would be able to see how we can. Okay. So once you do that and once you put that together, you would have some ideas so that you would be able to see what the basic elements are that are from one of the models that are not basically colliding spatially with another one. This is if you have, let's say, very, very large projects, a project that has many engineering disciplines, and you're still doing, let's say, sole BIM on various different aspects, you still need to know what elements are basically going to be not having any type of clashes with the other one. Because if you have spatial clashes, what is going to happen? You're not going to be able to build this, right? And you don't want to know this when you're on construction site. We have had situations like this as well, where, you know, the mechanical engine, and these are aspects that we right now take for granted. Well, we put it both together and then we take it from there. It's like, no, this wasn't the case, let's say 20 years ago. You actually didn't have tools this readily available. Some of these, let's say, EPC contractors for oil and gas, they did 4D simulation and clash detection from years ago, but they had their own custom-made software. Now you have basically a normal Navisworks that as students, you can take it and get it and perform this clash detection together. Now, is this clash detection correct? is it always going to provide you with the correct answer? And the answer to that, like every other software program, is no. There's always going to be variability and uncertainty. You can maybe say 90, 99%, 95% of the time is going to be correct, but you typically are going to always see type 1 errors or type 2 errors. Essentially, a clash that doesn't exist or a clash that does exist, but we incorrectly identify it as it doesn't exist. So type 2 errors is the dangerous one, right? Type 1 error is kind of like better safe than sorry, you know? But type 2 errors is basically where the hard part is. You know, if someone has a deadly disease, they don't want the lab report to say, no, you don't have it, you know? But if the lab report says you have it and they don't have it, it's better. It's not good, it's better, right? We can all agree with that. Okay. So this is the whole idea, right? You're always going to have type 1 errors and type 2 errors in these situations. Scientific work in this area is to minimize this, right? And the main reason why this is the case is because there's going to be some approximations in the spatial domain for us to be able to know what elements and what coordinates are going to be having what type of connections and communications with others. So it comes down to how spatial closeness or nearest neighbors are defined. And the solutions to those problems are, for the most part, heuristic. You would be able to get good results by utilizing, let's say, KD tree structures and OC tree structures, but there's some uncertainties there, and this could happen. Even to this day, it could happen, right? So this is something to be mindful. Requires some validation and rechecking. 4D scheduling, and this is what we talked about with respect to some other parts there. And for this, you have basically your elements. Now what you would need to do is you would need to assign for each and every one of these objects that are production activities, and it depends on the level of detail that you're going to be modeling this. And using the detail that you're going to be having, what type of, let's say, schedule and what kind of duration you're going to be assigning to each and every one of these activities. So it requires two basic aspects. One is the order of the activities, basically the work sequencing, and then the second part is the duration, right? Using that, you would be able to simulate it. And once you have that simulation, you can know more or less how this structure is going to go, and then you can have it in much more detail. If you, let's say, have temporary facilities here as well, temporary, let's say, elements, you can have shoring there, you can have the formwork. It depends on the type of, let's say, building that you have. You can model each and every one of these parts, right? And once you model it, that means that now you have a collaboration and agreement between whatever scheduling software and scheduling method you're utilizing, so the project management side of it, and whatever geometry is going to be built in terms of your production activities. So for instance, in this case, you have the beginning, you have the end, you would be able to see how the simulation is, and then take it from there. What this, at least in this current format that I looked into and put together, does not provide is that if the schedule in one of these, let's say, changes, everything else also in the future changes as well. That is something that requires some level of automation, some level of understanding of what each and every one of these connections and linkages are going to be. And these basically ideas are ideas that we're going to be utilizing in order to maximize the amount of automation that we're going to be having for each and every one of these. We want to have this in more, let's say, two-way communication manner. We can identify whether some element is not on schedule. For instance, one way is through point clouds and comparing these together. And that is also not, let's say, a done deal in terms of its scientific parts of it. However, we also are not utilizing that information to its fullest potential. Let's say we know this information. We know the earned value analysis in terms of project control. What is going to happen? What would be the best course of action to meet the project credentials? That also requires us to have good information, but we also need some sort of other aspect in order for us to be able to know what the proper course of action and the proper decisions are going to be in order to meet the project deadlines. And this is in terms of schedule. You can have it in terms of cost and various different aspects.